Okay, good morning. Lecture 18 in linear algebra. And I'm going to start with looking at some of the homework problems in section 4.3 on page 216, 217, and so on. And so this is some homework. This is pages 216 to 219 or so. Section 4.3 on bases for vector spaces and dimension. So in problem 1, we're looking at the vector space R2, and in section A, we have a set of two vectors, 1, 0, and 0, 2. And the question is to determine a basis for the subspace generated by the set. So in this case, it's easy because if you look at these two vectors, you can see that these vectors are linearly independent. You have C1, 1, 0 plus C2 times 0, 2. If that's the 0 vector, when you compute this linear combination, you get C1, 2C2. And that's equal to 0, 0 if and only if C1 is 0, 2C2 is 0, which is the same as C2 equals 0. So these two vectors are linearly independent. So they generate all of R2, and they form a basis. In fact, you can see, if you take any vector x, y, you can write that as x times 1, 0 plus y over 2 times 0, 2. If you calculate this linear combination, you get xy. So the subspace generated by S1 is in fact all of R2. Okay, so that's an interesting problem because it uses quite a few ideas of linear independence, the dimension, and bases. All right, any questions about that? Let's look at part B.
I have a quick question.
Yeah, go ahead.
On the bottom, the final answer, where it says x vector 1, 0 plus y vector 0, 2, is that
Y over 2, 1/2 of y.
okay? How did you get y over 2?
Well, so suppose the problem is to find scalars that say C1, C2, such that C1 times 1, 0 plus C2 times 0, 2 equals XY, right? We want to write XY as a linear combination of these two vectors, okay? You want to solve for C1, C2. Okay? Do you see that? That's what we have to do.
Okay, I see that, but
Okay, but what is this? If you write this out, so let's write this as XY equals this. So C1 times 1, 0 is C1, 0. And C2 times 0, 2 is the vector 0, 2, C2. And if you add these two vectors, you get C1, 2, C2. And you want that to be XY. So X has to be C1 and Y has to be 2C2. So C1 has to be X. If T2C2 is Y, C2 has to be half of Y. And that's how I got these numbers. X times 1, 0, plus Y over 2 times 0, 2 equals XY. I'm solving this vector equation.
So it's y over 2 because it's 2c2.
Because 2C2 equals Y, so C2 is Y over 2. Just solving for C2.
Oh, okay, I see it now.
Right. Okay.
And let me just take a picture of that.
Okay, but it'll be on YouTube, right after the talk over the.
Okay, okay.
Right. Okay. Let's look at parts, the rest of this, parts B and C and so on. So in 1B, we have a set S2 consisting of two vectors, 1, 1, and 1 minus 1. And again, these are also linearly independent. If you have C1 times 1, 1, plus C2 times 1 minus 1, if that's the zero vector, when you expand this, what is this vector? This is C1 plus C2, C1 minus C2. So C1 and C2 have to satisfy these equations that the first coordinate is 0 and the second coordinate is 0. And when you add these equations, you get 2C1 equals 0, so C1 is 0. And if C1 is 0, C2 is 0. So these two vectors are linearly independent. And so the subspace they generate is going to be all of R2. If you want to see that explicitly, you could say, well, suppose I want to write the vector xy as some linear combination of these two vectors. Can I find C1 and C2 that satisfy this equation? So this is C1, C1, and this is C2 minus C2. This is C1 plus C2, C1 minus C2. So if you equate the first coordinates, you get C1 plus C2 has to equal X, and C1 minus C2 has to equal Y. And then you have to solve the system of equations. And if you solve it, you get, if you add them, you get 2C1 is X plus Y, C1 is X plus Y over 2, and C2 is going to be X minus Y over 2. Right? I mean, I leave it to you to solve these equations, but there's this solution. And when you have this solution, you're done. So every vector is a linear combination of these two. So these form a basis. So S2 is a basis for the subspace generated by S2, which is all of R2. So I have a set of two vectors, 1, 1, and 1 minus 1. I want to find the subspace they generate and a basis for that subspace. So the first thing I do is I see that these two vectors are linearly independent. So they will automatically form a basis for whatever subspace they generate. They're linearly independent because if a linear combination of those two vectors is 0, then the scalars are both 0. That's the definition of linear independence. And I can write every vector in R2 as a linear combination of these two vectors. I do it by solving these two equations. So the subspace that these two vectors span is the entire vector space, R2. Let's look at parts C and D.
Professor, I didn't finish writing that. Can I take a picture? Oh. Okay, I'm done.
What about part 1C? Here I have a set S3 consisting of two vectors, 0, 0, and 1, minus 1. And these vectors are not independent. These are linearly dependent because, for example, 1 times 0, 0 plus 0 times 1 minus 1 is the 0 vector. And here in this linear combination, the scalars are not all 0. This is a 1. So these are linearly dependent. And the set of vectors they generate is just all linear, all scalar multiples. This is just all scalar multiples of 1 minus 1. And a basis, so a basis for this subspace is just the set consisting of 1 minus 1. The dimension of that subspace is 1. It's not 2, because this subspace is just has a basis with one vector. In fact, if you want to draw a picture of this, the vector 1 minus 1 in the plane, this is 1 minus 1, and the subspace is just this line through the origin. It's the line y equals minus x. That's the subspace that this set generates. It's all scalar multiples of 1 minus 1.
How did you know to multiply 1 by the vector 0, 0 and 0 by the vector 1, negative 1?
Well, I mean, first I can look at it and see that if I do that, if I have the 0 vector, no matter what I multiply it by, I get the 0 vector. I could have multiplied it by 7. It's the same thing. 7 times the 0 vector is still the 0 vector. So if I multiply this by any non-zero number, like 7, and I multiply this by 0, I'm still going to get the 0 vector plus the 0 vector equals the 0 vector. Once I see a set contains the 0 vector, I know that set is linearly dependent. You can't have a linearly independent set where one of the vectors is the 0 vector.
And can you explain S3 equals and then so on?
This?
Yeah.
So this notation, if you have any set, S is any set of vectors, this S in brackets is the subspace generated by S, which is the set of all linear combinations of vectors in S. We proved if you take any set of vectors and you look at all their linear combinations, that forms a subspace. So if you go back a few pages in the text, you'll see this theorem, right? Set of linear combinations of all vectors in any set is a subspace. So this means the subspace generated by these two vectors. So S3 is the set of all linear combinations, let's say C1, 0, 0 plus C2, 1 minus 1.
Yeah, I know it's referring to that, but I meant like the vector 1, negative 1. Why is it chosen to be written in the subspace?
Well, no. S3, this is what we start with. We're given the set S3, which contains two vectors, this one and this one. Right? That's what's given. So the subspace S3 generates is all the linear combinations. of those two vectors. That's the definition of the subspace generated by a set. But anything times the zero vector is just zero. So this is just zero. This is just the set of all linear combinations of all scalar multiples of 1 and -1. And I don't have to, I can use any letter. I just call it T instead of a C2. It doesn't matter, or X. Pick your favorite letter, but it's all scalar multiples of the vector 1 - 1.
Okay, now I understand.
Any other questions? Okay, in part D, we have a set S4 consisting of 1, 1, 1 - 1, and -1, 1, contained in R2. So this set contains 3 vectors, but R2 has dimension 2. So the largest set of linearly independent vectors in R2 is going to have 2 vectors. So this set has to be linearly independent. So I know that even from the start, but if I want to show that exactly, I need to show there's a linear combination of these vectors, which gives 0. Now, I could think up one pretty easily, or I can just do it in a more systematic way. So suppose I have the 0 vector is some C1, 1, 1, plus C2, 1 - 1, plus C3 - 1, 1. Whereas if I calculate this linear combination, this is C1 plus C2 minus C3, C1 minus C2 plus C3. So the scalars, C1, C2, C3, have to satisfy the equation C1 plus C2 minus C3 equals 0, C1 minus C2 plus C3 equals 0. So we have to solve these equations. Let's see. If you add these equations, you would get 2C1 equals 0. So C1 has to be 0. But then you have C2 minus C3 equals 0. So C2 equals C3. So I can let C2 and C3 be any number. I don't know, like 7. Doesn't matter what, 7. Or 5 million. It doesn't really matter what you take. Just take some number. If you have 1, 1 plus 1 - 1 times 7 plus 7 times -1, 1. Sorry, and 0 times that. C1 is 0, C2 and C, these numbers are the same. You get 0 plus 7 minus 7, 0 minus 7 plus 7, you get 0, 0. In any case, this is a linear combination where not all the coefficients are 0. One of them is 0, but 2 of them are not. So that proves that S4 is a linearly dependent set. In fact, if you look at this, the vector 1, 1 can be written as 1 - 1 minus -1, 1 times a half in each of them. Just if you actually do the calculation, this is equal to a half times the vector 1 - 1 minus a half times the vector -1, 1. You add that up, you get 1, 1. So this shows 1, 1 is a linear combination of these two vectors. And these two vectors, any two of them, in fact. So, for example, 1 - 1 and -1, 1 are linearly independent. So S4 generates R2, and the basis is just the set of these two vectors. Right? Remember, what is the basis for a subspace? It's a linearly independent set of vectors that generates the subspace. So if you have any linear combination of these three vectors, I can replace 1, 1 by a linear combination of these two. So any linear combination of these three vectors is a linear combination of these two vectors. And those two vectors are linearly independent. So that's what we needed
Can
to
you move
show.
up the paper a little bit up? I have a question.
Okay.
Where you see a vector, can you explain a little bit to the right-hand side? Okay, no, after it says 7, 4 is linearly dependent set, below that, can you
S4.
explain? Yeah,
This.
S4.
Yeah.
Can you explain that part where it says vector 1, 1 equals 1 over 2 and vector,
Minus.
yeah, that
So
one.
this is not 1 over 2, it's a half.
Yeah,
This is a half times 1 minus 1, minus a half times the vector minus 1, 1. So if you do the arithmetic, is this correct? You just calculate the linear combination. And this is what you get. So this is a true equation. It's like saying 1 equals a half plus a half. I mean, that's a true equation. This is a true vector equation.
how did you know that that you should use a half?
I just did the arithmetic in my head. But you could also do it as follows. You could say, suppose you want to write 1, 1 as some linear combination of 1 minus 1 plus minus 1, 1. Okay? So this is x minus x plus minus y, y. That's x minus y minus x plus y, y. Minus x plus y. So you want to find x and y such that this equals 1, 1. So you're solving the equations x minus y equal 1, minus x plus y equals 1. Let me just double check. X minus x minus y, x minus y minus x plus y. So let's see, something here isn't correct. So let me look at this again. Oh, sorry. I'm just double checking my arithmetic. What's going on here? Oh, I'm sorry. Thank you. So actually, I made a mistake. That's good. So let me start this problem from the beginning. So there's but a mistake is a mistake. So S4 consists of the vectors 1, 1, 1 minus 1, and minus 1, 1. And I want to show these vectors are linearly dependent. So I gave an example. If I took 0 times 1, 1, plus 7 times 1 minus 1, plus 7 times minus 1, 1, I get 0, 0. So therefore, this set is linearly dependent. In fact, if I had looked a little more carefully, I would have noticed that the vector 1 minus 1 is actually a scalar multiple of the vector minus 1, 1. It's minus 1, 1. So these two vectors themselves are linearly dependent. So if I want to look for a linearly independent set, let me take the first two vectors. So I have 1, 1, and 1 minus 1. And
Where it says notice, how did you get negative vector negative 1, 1?
how did I get this equation?
The answer, the negative on the outside of the vector.
Well, because it's true. Minus this vector is this vector. Right? You know, what is minus 1, 1? This is minus 1 times this vector. That's minus 1, minus 1. Minus 1 is plus 1, so it's 1 minus 1. So the negative of this vector is this. Or if you like, if you add 1 minus 1 and minus 1, 1, what do you get? You get 0, 0. So 1 is the negative of the other.
Okay.
Right? But I claim these two vectors are linearly independent. And in fact, I already did that. That's the set. This is in 1B. That was the set S2 in part B. So I know these two vectors are linearly independent. So the subspace these three vectors generate, it still is all of R2, and a basis is this set of these two vectors. If you have a set of vectors that generates, a basis is the largest subset that's linearly independent. And these two vectors are linearly independent. So there are sort of like basic concepts you have to understand to do these problems. You have to understand what is linear dependence and independence. You have to understand the concept of a basis for a subspace. And you have to understand the concept of the dimension of a subspace. This is all, I mean, that's exactly what this section is about, but this is sort of fundamental linear algebra. Okay. Any questions about problem 1 before I go on to problem 2? So in problem 2, I'm looking at there's a typo. It says subspaces of R2, but if you look, we're clearly looking at subspaces of R3 because all of our vectors are three-dimensional. So we have the set in part A of problem 2, the set S5, which consists of the vectors 2, 0, 0, 5, 0, 0, and minus 1, 0, 0. And if you look at this, you see each of these vectors is a scalar multiple of every other vector. So for example, 2, 0, 0 is, if you take the vector 5, 0, 0 and multiply it by 2/5, this is what you get. Or if you take the vector minus 1, 0, 0 and you multiply it by minus 2, you also get 2, 0, 0. Each of these vectors is a scalar multiple of the other. And
Are you choosing 2/5 and -2 by choice?
no, I have no choice. If I want to write this vector as a linear combination of this vector, The only number that works is 2/5,
Okay.
right? If I want to write 200 is some x times 500, that only happens when x is equal to 2/5. There's no other, I have no freedom about that at all. That's forced on me.
And it's the same thing for the vector 2, 0, 0 equals -2, like 2 and -1, there's only the
Yeah,
-2.
I mean, if you're solving the equation 2 equals x times -1, x has to be -2. Right? There's no choice.
Okay, thank you.
And so these three vectors, not only are they linearly dependent, but each is a scalar multiple of each of the others. So the subspace generated by S5, any one of these can be a basis. So this has a basis. You can choose any one, like 200, for example. And the dimension of this subspace is 1. You have a basis that contains just one vector. So that means, so that by definition, that subspace has dimension 1. So S5, that set S5, even though it consists of 3 vectors, it generates a one-dimensional subspace.
I have a question.
Go ahead.
The answer that you circled, how did you get that?
I'm not this.
Right above.
This.
Yes.
2 equals x times -1. What does x have to be?
Oh, okay, I see that for.
Right.
Okay.
Okay. Let's look at part B. Part B, we have another set, S6, that consists of 3 vectors, 200, 500, and -130. Now, again, these 3 vectors are linearly dependent because these 2 vectors, each is a scalar multiple of the other. So this is a linearly dependent set. On the other hand, but the subspace they generate, what's the largest linearly independent subset? If I take the set consisting of, let's say, the first and the third vectors, 200 and -130, these 2 vectors, so this set is linearly dependent, but this set is linearly independent. Because if you have a scalar multiple of them, if 000 is x times 200 plus y times -130, what does that tell us about x and y? So you compute this linear combination. X times 200, that's 2x 00. And y times this factor is -y 3y0. And if you add these vectors, you get 2x minus y, 3y0. And that's going to be 0, 0, 0. But then 3y has to equal 0, which means y equals 0. And 2x minus y equals 0. But y is 0, so 2x equals 0. So x equals 0. So the only linear combination of these 2 vectors that produces the 0 vector occurs when both x and y are 0. So that means these 2 vectors must be linearly independent. So this is the largest linearly independent subset of this set. So this is the basis. And so the subset generated by this set of three vectors is two-dimensional. It has a basis consisting of two vectors. So S6 generates a two-dimensional subspace.
You said S6 equals a two-dimensional subspace?
No, I said the subspace generated by S6, that's what this means,
Hmm.
is the dimension of this subspace is 2. S6 generates a two-dimensional subspace because it has a basis consisting of two vectors. And the two vectors are these two. This one and this one.
Okay, thank you.
Let's look at part C. So S7 is a subset consisting of three vectors. 6, 9, minus 3, minus 4, minus 6, 2, 1, 2, 3. And we want to find the subspace these three vectors generate and the dimension of that subspace. So let's do it the old-fashioned way. Suppose the 0 vector is a linear combination of these three vectors. So x times 6, 9, minus 3 plus y times minus 4, minus 6, 2 plus z times 1, 2, 3. When you write out this, when you compute this linear combination of vectors, you get the vector whose first coordinate is 6x minus 4y plus z, 9x minus 6y plus 2z minus 3x plus 2y plus 3z. So to say that this vector equals this vector is the same as saying x, y, z is a solution of the system of homogeneous equations 6x minus 4y plus z equals 0, 9x minus 6y plus 2z equals 0, minus 3x plus 2y plus 3z equals 0. So we're reduced to solving three equations and three unknowns. So you can solve those equations any way you like. Let's say I want to do it by taking the matrix of coefficients, 6 minus 4, 1, 9 minus 6, 2, minus 3, 2, 3, and writing this in as the matrix and put it in reduced row echelon form. So let's see. Let me do it. I'll do it. I mean, and you can do it any way you like. Let me interchange the first and the third rows. And if I take the first row and I add twice the first row to the third row, I get a lot of cancellation. Minus 6 plus 6 is 0. 4 minus 4 is 0. So I'm taking minus 2 times this plus this. Minus 6 plus 3 is minus 3. And if I add 3 times the first row to the third row, I get 0, 0, 11. Huh. And so this is minus 3, or let me, if I want, I can divide the first row by minus 3.
Professor, is it possible if you write the notation on the arrows, just so we can have it in the video?
Well, here I'm just interchanging the first and the third rows,
Okay.
right?
I'm just supposed to put the
Oh,
zero
sorry.
column at the end.
6 for this should be a 1. Right? I'm interchanging the first and the third rows. Right? 6 minus 4, 1. 9 minus 6, 2. Minus 3, 2, 3. And when you interchange the first and the third rows, this is what I get. And then if I add 3 times the first row to the third row, I get this. And if I add 2 times the first row to the third row, I get a 7. So I'm just row reducing the matrix. If I take the first row and I divide by minus 3, I get 1 minus 2/3 minus 1. And if I take the second row and I divide by 11, I get 0, 0, 1. And if I take the third row and I divide by 7, I get 0, 0, 1. And if I take the third row minus the second row, I get 0, 0, 0. If I add the second row to the third row, I get 1 minus 2/3, 0. So, well, I mean, you can do this any way you like, but at this point, you have to know how to put a matrix in reduced row echelon form. And that's what I've done. So this is in reduced row echelon form, if I haven't made too many mistakes in arithmetic. So this is, so an equivalent system of equations is x minus 2/3 y equals 0, z equals 0. So if I'm solving these equations, x is equal to 2/3 y and z is 0. So for any solution of these equations, x, y, z, x is 2/3 y, y 0. This is y times the vector 2/3 1, 0. So, for example, for that y equal 3, I would get x, y, z equals 2, 3, 0. So if I look at these 3 vectors, this tells me I have a non-trivial linear combination. If I take 6, 9 minus 3 times 2 plus minus 4 minus 6, 2 times 3 plus 0 times 1, 2, 3, I get the 0 vector. And if you check the arithmetic, this is completely correct. So these are my scalars, 2, 3, 0. They're not all 0. So these vectors are linearly dependent. In fact, these 2 vectors are scalar multiples of each other.
Did you skip steps to get vector 0, 0, 0?
Did I skip steps?
Yeah.
to get to here?
Yeah.
No. I solved these equations for x, y, and z. All right. X, y, z can be any multiple of 2/3, 1, 0. So if I let y equal 3, for example, I get 2, 3, 0. So I'm taking x equal 2, y equal 3, z equals 0. And this linear combination gives me the 0 vector. Right, again, I started with these 3 vectors. And I asked the question, are these vectors linearly independent or not? So I want to know what scalar multiple, what linear combination of those 3 vectors would give the 0 vector. So what vector, what x, y, and z will solve this vector equation, which is the same as this equals the 0 vector, right? It's all equal to the 0 vector, which means x, y, and z satisfy this homogeneous system of linear equations. So I need to solve that system. And I can do it any way I like. I'm choosing to do it by taking the matrix of coefficients and putting it in reduced row echelon form. And when I do, I get this matrix. So, and corresponding to this matrix is this system of homogeneous equations. There are only 2 of them. And the solutions of this system are all x, y, and z that are scalar multiples of this vector 2/3, 1, 0. So just to get rid of the fractions, I can choose y equal to 3. I get 2, 3, 0. So if x is 2, y is 3, z is 0, I have a solution of these equations, which means a solution of this vector equation. So I'm not skipping any steps. I found that 2, 3, 0 produce the 0 vector. And that says that these vectors are linearly dependent. So that tells me that this set S7 is not a basis for the subspace that's generated. In fact, this vector is a scalar, the first vector is a scalar multiple of the second. On the other hand,
How did you
Right.
get vector
What?
6, 9, -3?
sorry,
How did you get the vector 6, 9, -3 on the bottom?
S7 consists of these 3 vectors. This is what,
Okay, there's
this
just
is
a
the
given.
problem
Okay, my
that I'm
fault.
given. These are the 3 vectors. I'm not making them up. Solve this problem. Here's a set of 3 vectors. Find the subspace they generate and find a basis for it and find the dimension of it. So these are the 3 vectors. And these are linearly dependent. So I can throw one of them away. Now I see that, for example, the vector 6, 9, -3 and the vector -4, -6, 2, one's a scalar multiple of the other. If I multiply this by -3/2, I get this. So these 2 vectors, one's a multiple of the other. So I can just like throw one of them away. And I can look at these 2 vectors. The vectors -4, 6, 2 and 1, 2, 3. So these 2 vectors, this is a subset of the set S7 that I started with. And these are linearly independent. I can check that. Again, if you write down x -4, 6, 2 and y times 1, 2, 3 equals 0, 0, you'll see the only solution of this equation is x equal y equals 0. So this forms a basis for the subspace generated by S7, and the dimension of that subspace is going to be 2. Okay. Let's look at problem number 3. On page 217. We have a set B consisting of 3 vectors, which we're told are linearly independent. V1 is 1, 1, 0. V2 is 1, 0, 1. And V3 is 0, 1, 1. So we're given the vector V. This is what we're given. And we're not inventing anything. We're given the vector 3, V, which is 3, 4, 5. And we say that the coordinate vector for V with respect to basis B is, let's say, x1, x2, x3, if x1, v1 plus x2, v2 plus x3, v3 equals V. So if you have a basis for a vector space, the coordinate vector for a vector V with respect to that basis is the set of coordinates that you come up when you write that your vector as a linear combination of the basis vectors. So let's write this out in coordinates. This means that what is x1, v1 plus x2, v2 plus x3, v3? That's x1 times 1, 1, 0 plus x2 times 1, 0, 1 plus x3 times 0, 1, 1. What is this? This is x1, x1, 0 plus x2, 0, x2 plus 0, x3, x3. That's equal to, when you add it up, x1 plus x2, x1 plus x3, x2 plus x3. That's what a linear combination of these 3 vectors look like. And we want to choose the linear combination that produces the vector V, which is 3, 4, 5. So that's the same as saying that x1, x2, x3 solve this system of inhomogeneous linear equations. x1 plus x2 equals 3, x1 plus x3 equal 4, x2 plus x3 equal 5. So we must solve this system of linear equations. But let me pause for a minute and give you a chance just to look at this so you understand how the problem is set up, right? This is what we do so we can start to solve the problem, right? We haven't solved the problem yet. We want to be able to express the vector 3, 4, 5 as a linear combination of these 3 vectors. That means that this equals 3, 4, 5. And again, how we solve these equations is up to you. You could write down the augmented matrix and put it in reduced row echelon form, or any other way. For example, if I take the first equation minus the second equation, I get x2 minus x3 is 3 minus 4 is minus 1. And the third equation was x2 plus x3 equal 5. And if I add, I get 2x2 equal 4. So x2 is going to have to be 2. And if x2 is 2, this says that x1 plus 2 equals 3, so x1 has to be 1. And this says that x1, which is 1, plus x3 is 4, so x3 has to be 3. So x1, x2, x3 is the vector 1, 2, 3. That's the coordinate vector of V with respect to this basis. That is, if I take 1 times V1 plus 2V2 plus 3V3, 1 times V1 is 110, 2V2 is 202, 3V3 is 033. When I add that up, in fact, I do get 345. So this is kind of my check.
How did you get 9 where it says 2x to the second power equals 9?
Where is that? Oh,
To
here?
the, yes.
Sorry, no, that's a 4.
Oh, that's a 4, okay.
Minus 1 plus 5 is 4.
Okay.
So x2 is 2.
And then can you explain in the middle x1 plus 2 equals 3, then x1 equals 1 on the bottom in the middle?
Here?
Yeah.
So this says x2 is equal to 2. Right? Right? x2 equals 2. Another equation is x1 plus x2 equals 3, but I just found that x2 is 2. So this is the same as saying x1 plus 2 equals 3, or x1 equals 1. I'm just solving these equations, right? When you reduce a problem in linear algebra to solving linear equations, that's supposed to be the easy part, because we spent a month learning how to solve systems of linear equations.
All right.
Okay, well, let's look at 4 and 5. Then we have problem 4. This is now on page 218. So we have W1 and W2 subspaces of Rn with W1 contained in W2. We want to prove that in fact these two subspaces are equal if and only if they have the same dimension. So it's sort of like, here's our picture, here's Rn, and sitting in Rn you have W1, and you have a bigger subspace W2 that contains W1. And we want to show they're equal if and only if they have the same dimension. So, of course, if W1 equals W2, then any basis for W1 is a basis for W2, so they have the same dimension, because the dimension is the number of elements in a basis. So that's the proof that this implies this. And what about the proof going backwards? So suppose dimension of W1 equals dimension of W2. Suppose it's equal to some number k. So if the dimension of W1 is equal to k, then W1 has a basis B, which consists of k vectors. Which are linearly independent. And if W1 is a proper subset of W2, then, so we already proved this, if you have a subspace contained in a bigger subspace, and you have a set of vectors that generate the subspace W1, then you can always find some other vector in the bigger subspace that's linearly independent from the previous one. So then there exists a vector called Vk plus 1 in W2 such that the set of vectors V1, V2 up to Vk with this new vector key plus 1 adjoined is linearly independent. Which means that the dimension of W2 is at least k plus 1, which is false, because the dimension of W2 is k. So W1 cannot be a proper subset of W2, it has to be equal. But again, this argument depends on having studied carefully the material in this section. Right? So in this section is lemma 4.3 on page 214. That's what it is. I'll go back and review some of the material, but I just want to do this last problem and then I'll go back. Okay. This is the solution to problem 4. And what is problem 5, which was the last problem in this section? So in problem 5, we have in R3, W1 is the subspace generated by the vectors 1, 0, 0 and 0, 0, 1. So if you're looking at R3, let's say this is X, Y, and Z, 1, 0, 0 is the x-axis. Right? The x-axis is all scalar multiples of 1, 0, 0. 0, 0, 1 is the z-axis. And if you look at all linear combinations of a vector in the x-axis and a vector in the z-axis, you get the xz plane. So a description of the subspace generated by W1 is the xz plane in R3. Because if you look at any linear combination, x1, 0, 0 plus z, 0, 0, 1, you get all vectors x, 0, z. That's all vectors where the y coordinate is 0, which means the xz plane. Just note that. Okay. In part B, we have a different set of vectors in R3. It's the set of vectors 1, 0, 0 and 1, 1, 0. What are those vectors? So this is the x-axis is generated by 1, 0, 0. In the YZ plane, 1, 1, 0, that's just the line. It's just like a line, x equal y in the YZ plane. So the subspace generated by the set W2 is the XY plane in R3. Every vector in the plane is a linear combination of these two vectors. But you can write any vector x, y, 0 as, if you want some linear combination of these two, it's going to have to be y times 1, 1, 0, which means this is going to have to be x minus y. So every vector where the z coordinate is 0 is a linear combination of these two vectors. So W1 is the xz plane. W2 is the yz plane. Actually, well, yeah. In part C, it asks, what is the intersection of these two? So if you think about this geometrically, W1 is the xz plane. W2 is the xy plane. They intersect in the x-axis. It's that line through the origin. That's the intersection. And in part D, W1 union W2, I should have said the subspace they generate. That's all of R3, but it's a typo. Now, if you look at W1, that's a plane. The dimension of W1 is 2. W2 is another plane. The dimension of W2 is 2. The intersection is a line that has dimension 1. And the dimension generated by the union is 3. And it just says to observe that 3 plus 1 equals 2 plus 2. Right? That's the dimension W1 union W2 plus the dimension of W1 intersect W2 is dimension of W1 plus dimension of W2. That's, so all that is saying is confirm that 3 plus 1 equals 2 plus 2, and I assume everyone knows this. Okay. So let me go back and look again at some of the theorems in this section that we use here. So this is a section with a lot of meat. So this is section 4.3 on bases and dimension of subspaces. So the first theorem that I proved last week says that if S is a set of M vectors, so this is a finite subset of a vector space V, and W is the subspace generated by S. So all linear combinations of vectors in S. If I take V1, V2 up to Vn, any vectors in V, so any vectors in W, the subspace generated by this. If N is bigger than M, then this set of vectors, V1 up to Vn, is linearly dependent. And if the set of vectors is linearly independent, then N is less than or equal to M. In the note, it said N strictly less than M, but that was a typo. This is exactly what it's supposed to be. And the next result, theorem 4.8, says that if S is a set of vectors, not the zero set, so this is a non-empty finite subset of a vector space V, and W is the subspace generated by S,
Yeah.
then S always contains a subset that is linearly independent. So S contains a linearly independent subset that generates W. So this result we used in the exercises. And we have, for example, a set of 3 vectors that generated a subspace. The vectors were linearly dependent, but we could always throw away some vectors and be left with a linearly independent subset that generated the same subspace. That's theorem 4.8. And this gives us the definition of a basis. A basis for a subspace is a linearly independent set of vectors that generates the subspace. So a basis for a subspace is a set of vectors with the following 2 properties. Every element, every vector in the subspace is a linear combination of vectors in the basis, and the set of vectors in the basis is linearly independent. And one of the great theorems in linear algebra says bases for a fixed subspace have the same number of elements. All bases have the same number of elements. And another name for number of elements is cardinality. So the cardinality of a basis for a subspace depends on the subspace, but you cannot have two bases that have different numbers of elements. So that is a big deal. And this number is what is called the dimension of the subspace. All bases have the same cardinality, and that cardinality is the basis for the subspace.
Check on their uncovered panel or under do that. Might is calling on topic. Yeah.
Can someone mute themselves right now? Thank you. Okay. And another theorem that we use in the exercises says the following. This is theorem 4.11. So you have a vector space V, a subspace W containing a smaller subspace W1. And so we have subspaces W1 contained in W2 in the vector space V. And if the dimension of the small space is K1, and the dimension of the larger space is K2, then K1 is less than or equal to K2. That is, if you have a bigger space, the dimension can only get bigger. And if V1, V2 up to V sub K1 is a basis for W1, then you can add vectors to that basis to get a basis for W2. So then there exist vectors V sub K1 plus 1, VK1 plus 2, up to V sub K2, such that V1 up to VK1, VK1 plus 1, all the way up to VK2 is a basis for W2. So this is this very nice result about bases. And there's one final result, which is the following. This is theorem 412. This also came up in the exercises. Here we have W1, W2 subspaces. This is the intersection, W1 intersect W2. And then we have the sum of those vector spaces, W1 plus W2. All vectors that can be written as the sum of something in W1 plus something in W2. And there's this very nice relation that says the dimension of W1 plus W2 is equal to the dimension of W1 plus the dimension of W2 minus the dimension of the intersection. So these are the big results in section 4.3. And these are very, very, very important results in linear algebra. So it's worth spending a lot of time studying this section. And of course, to understand what's in the section 4.3, you're going to have to know what's in 4.1 and 4.2. But this is all essential linear algebra. This will come up over and over again and in the second midterm and the final exam as well.
Do you know when is the second midterm?
End of November, beginning of December. You'll have a couple weeks notice. Thanksgiving is fairly early this year. Thanksgiving is the 23rd, so it's either the week after Thanksgiving, which is still November, or the very beginning of December. We'll see.
Professor, I'm sorry, my mic cut out. Can you repeat that one more time?
The second midterm will either be, it'll be after Thanksgiving, so either the last week of November or the first week of December. But you'll have at least 2 weeks notice and a review sheet as well.
Okay, thank you so much.
Sure. Okay. Other questions? Okay.
Oh yeah.
So
Will you be posting the lecture? Because I think you forgot to post lecture 16.
I posted it earlier today. It's up there now.
Oh, okay. Okay. Thank you.
And I'll post this in a few minutes. As soon
Okay.
as I log off and the software converts it into a uploadable file. Okay, all. See you on Wednesday. Enjoy the day. It looks very nice.